essentially, this is not, okay, let us go to the final result. The final result is that the Q parameter is given by this. This is the probability P for the flipped random variable. So you see, it is really an index, a numerical index of asymmetry. Okay. This is an anticipation on what I will say tomorrow, but it's very simple because you simply commute the concrete representation of the matrices. And let me go arrive to this point. You remember that when we discussed the Heisenberg commutation relation, here there was minus. Okay? Now we see that when we go to Bernoulli, there is plus. Now the problem is, this is true if we have one Bernoulli process. What happens if we have more? With the plus, they are very famous relation in physics. They are called the canonical anti-commutation relation. And they distinguish fermions by Bosons. So, for the Bernoulli random variable, we have the analog of what I mentioned, but I did not prove in this morning, of what we have for the Gaussian random variable, but with plus. For the Gaussian, you have minus and the variance. For Bernoulli, you have plus and the variance. Now, but this is for one variable. For two variables, in general, you have many possibilities, even for two. If you go to n fermions, you have a lot of many more possibilities. What Professor Lu did this morning is to show, without speaking of physics, to classify all possibilities that you have for two fermions. Among them, there is only one. That is the one that the physicist took, because it fits with the experimental data. And it is the one which, as yes, Professor Lu explained this morning, in which P is exactly, P is 1/4, if I remember. Okay. So they correspond to essentially the independence. If I remember well, I may be wrong now. But what is it? The canonical is boson. Canonical commutation relation, CCR.
He said does it have anything to do with canonical quantization?
This is Fermi quantization. This is Fermi quantization. But for one variable. What do you need for a single fermion? What do you need to go to many fermions? Here there is a deep new idea. And this is why, in some sense, even if Fermi correspond to Bernoulli, which is much simpler than Gaussian, because it's two values. Gaussian is continuously valued. But, and so, tomorrow we will see how Gaussian come out. But here, you can ask yourself, what do we need to obtain the full description of Fermi in many, many particles, in the case of many fermions? Okay? So the answer is the following. you need a very deep physical principle, which is called the Pauli principle.
It's called what?
Pauli principle. Pauli was a famous physicist. Surely, if some physicists is here, they know very well the name of Pauli. And probably the most famous of his result is exactly this, which is essentially the philosophy is that bosons are, how to say, very sociable particles because they tend to aggregate. Fermions tend to separate from each other. You see?
Sorry. The Vsn here, what's the n plus n minus? N plus n minus
N plus is the representation of the creator in the toy box space. And minus the representation of the annihilator.
Okay.
The diagonal part is the preservator. Always. So this is the off-diagonal part. Creator and annihilator are off-diagonal. And the diagonal is preservator.
So the 59, what's its relation with the CAR?
Yeah, and the share. In the physics, you typically take the variance equal to 1 or 2 h bar equals.
Yeah.
Right. Okay. So, according. But what I was saying, now this, I cannot give the proof of this, how to deduce the analog, what is the analog of this computation when we have many variables. Then, and Professor Lu described in the one parameter family. Professor Lu considered the case of only 2 families. So, what is the analog of this in the case of 2 fermions? If you have 2 fermions, you have 2 creators, 2 annihilators. Then in Professor Lu lectures were A1, A dagger 1, A2, A dagger 2. So, in this case you have A1, A dagger 2 plus A dagger 2, A1, which is exactly this, is not 1 but 0. Roughly speaking, the different degrees of in the boson case, we will arrive to this, and there is a very deep probabilistic meaning. In the boson case, in physics, they suppose that different degrees of freedom compute. Here, different for Fermi, different degree of freedom enter. Okay?
Why is the degree of freedom not equal to 1?
In equal to 1, you have only 1. You cannot anti-commute with yourself because this is only 0 operator. Because if A2 is equal to 1, only the 0. You have a positive operator, which can be equal to 0 if it's 0 identical. So it's not interesting. It's a trigger. So this relation has a meaning only when you have at least 2 parts. The non-trivial point is that if you assume Pauli principle, you deduce this. This is non-trivial and is a result of quantum.
Is it because you are coming from the point of view of physics? Because I know that for commutation relations, it should be A minus A dagger minus A plus A minus A dagger A.
Alright, and that is a boson.
Why are you okay?
No, but this is deducible.
Okay. So
the theorem, let me tell you the theorem.
Okay.
The theorem is this. Suppose that I formulate for 2 fermions, but the same thing goes for any number of fermions. Okay? If you put Pauli principle, what does it mean? It means that you cannot have a quantum state in which the two different fermions have are in the same quantum state. When you have 2 particles, you can speak of the state of the composite system, 1, 2. And then you can speak of state of the 1 and state of 2. And the Pauli principle says, if you have state 1 and state 2 equal, then this is forbidden. This corresponds to the zero state. Okay? So, the non-trivial point that I will not discuss here is that you can deduce that if you put this principle, that two fermions cannot be created in the same state, then you deduce the commutation. But in physics this was not deduced. This was postulated. And then Dirac gave a mathematical, that is why we call Fermi-Dirac. Because Dirac gave the mathematical, Fermi gave the physical.
Physics, yes.
The analog of the statistics, of the Bose-Einstein statistics. That is called Fermi-Dirac because Dirac did the mathematical. Okay?
Sorry, Professor.
Yeah.
I think there is a case in which this is having I, imaginary number. Yes.
No, this is the anti-commutation. This means that A1, this in the physics language, they use this symbol for the anti-commutator.
No, that's for CCR.
CIR. This is the CIR. CIR.
This for CCR.
Yes.
And the CCR is the commutation.
Usually,
Yeah, usually competition rate.
brackets. Yeah.
Yes.
However, we will discuss this in my future lecture
Yes.
to show that this, what the physicists consider as obvious, as a definition of boson, is in fact very, very strong condition on the random variable, the joint random variable. But this is a more...
CCR is remaining.
Yes.
Well,
So one can get this Poisson algebra from CI.
one can get...
The Poisson algebra. You are right. Yeah, because we did that thing.
What do you mean one can get? Poisson, this is an algebraic relation. Poisson is a probabilistic notion.
Yes.
You see? So, it is from this you can construct states which have Poisson distribution. And these are very famous states in quantum physics. They are called
Poisson bracket.
no, Poisson bracket is classical
It
mechanics,
is classical.
and it is in phase space.
Yes.
But here we are positioned.
Oh, yeah.
You see, L2 is complex, but we are in L2 of the position space. But the Poisson bracket are on the phase space.
Yes.
Position and moment.
Yes.
So, you see, this is the full, this is the most important point, which is, I will speak tomorrow, and I want to say, this is why the probabilistic approach gives much more than the physics approach. Because in physics, they define Fermi in terms of the anti-commutator. But in the probabilistic approach, we have much more, because we have the full multiplication theorem. You see, anti-commutator is a corollary of the multiplication theorem.
Yes.
Because if I know this product, and this product separately, of course I can compute the sum. Okay? But not conversely. If I know the sum of two numbers, even for numbers is wrong. Imagine for operator. So this multiplication table is much more than an anti-commutation equation. Okay? And I listed just for your knowledge, but you can read and try to understand this multiplication table, and from that we deduce the anti-commutation. Okay. But now we have also A0. This is a new with respect to physics. In physics, usually A0 is not considered. Okay, now I have finished the okay. Now what I want to and there was another question to Professor Lu this morning about the marginals. And you asked about marginals. Let me, we decided to speak of this idea, of this example of two Bernoulli, which is very simple. You can do the calculation totally explicitly, but it hides very, very deep message. And I will try to make it explicit.
You want marker?
So the point is because what in probability theory they call coupling essentially is you should intuitively think that the physics analog of coupling is interaction. So you have two probability measures. So you have M1 and M2. Let me take the general definition. And they are probability measures on the real line. But remember, for us, probability measures means probability measure with all moments. Remember the notation that I introduced this morning.
So the total measure on the quantity.
Yeah.
Now, these are probability measures on R. So now let us define a coupling. In fact, in the literature, you find coupling or copula or, but I would prefer to call it stochastic coupling because there are many other terms. Stochastic. Coupling mu1 and mu2 is a probability measure not on R. Not on R, but is a probability measure, always with all moments, not on R, but on R2, R times R. Such that, I repeat what was written in blue transparencies this morning. You see, the probability measures on R times R. What is R? What is the sigma algebra of R times R? Are they? We can take the intervals. A B
Cross.
times B prime B prime.
Yes.
This sigma algebra generated by this interval will be the sigma algebra of the product space, but not all measures on the product space are product measures.
Of course.
Of course.
That's right.
There is only one class of measures, which is called the product measure, which correspond to independent random. So independent random variable correspond to product measures. In physics, product measures are what we call statistical independence in probability in physics, they call absence of interaction. There is no interaction. So it's not so interesting from the physical point of view, because physics want to study interaction of physical systems. Okay? So let us now abstract the mathematical essence of this measure of interaction. So a stochastic coupling, so this I am defining stochastic coupling, is a probability measure such that, you see, I must give a probability measure on R2 is defined when I give the measure of all these intervals. So a subclass of this is the intervals which have the form A, B, times, and here I take all real lines. So what is probabilistic interpretation? Probabilistic interpretation of this is the probability. So mu1 and mu2 correspond to random variable x1 and x2. So this is the probability that x1 belongs to AB,
Yes. X2.
and x2 belongs to A prime, B prime. This is called in probability theory the joint probability. If A prime, B prime is equal R, then this is called the marginal. Let us call more precisely the first marginal. This is the first marginal. And this is the second marginal. R times A prime, B prime. Second marginal only. Okay? Now, mu is a stochastic coupling if the first marginal is equal to mu1 of AB and the second marginal is equal to mu2 of AB. No, A prime, B prime. So this is the notion of mapping, of coupling. Extreme case. So you may say, okay, you have given a definition, but maybe you can define the empty set. How do I know that what I defined is not the empty set? I know because the set of coupling at least has the product coupling. Extreme case, product coupling. The product coupling is denoted by this M1 tensor, M2, and this is the measure which to the interval AB times A prime, B prime associates the product. M1 AB times M2 A prime. So the product corresponds, and the product measure, we know from probability measure theory that this is the case, this is the probability distribution. This is called the joint probability distribution. Joint probability distribution of the pair x1, x2. If x1, if and only if x1 and x2 are independent. stochastically independent. Okay, so you see, the extreme case shows that the set of couplings is non-zero, is not empty. But it exactly characterizes independence. And we have seen that in physics, independence means absence of interactions. So independent is very nice and important to mathematical, and many things you can do with it. But the real interest is to study dependence on a number. For example, you know what is the what is the most famous example of the dependent random number? Have you, in classical probability, not in quantum, in classical, what is the most famous? Markov measures the most famous example. And you have, we have many other examples of multidimensional measures. You see, many. However, we have not a similar theory we have not a principle to use them to construct them. And I will come back on this. I hope I will have time to speak on this. So, why this coupling is so important? And we understood this quantum decomposition in what we will call analog of boson case, essentially between 1998 and 2016. However, only in 2023 we understood the meaning for physics. Why? Because, and this was conceptually for us a very important jump, because we understood that what in physics is called the Pauli principle is just an algebraic formulation of calculus. This I have formulated analytically in terms of measure. But using the quantum decomposition, you can formulate the couplings in algebraic language. And this is the object of Professor Ezekiel. He will describe to you how to create non-trivial interaction between measures. You can imagine that when you have a product measure, you have two random variables, so you have two particles, and so you want to describe interaction. What he did today is to describe all possible interactions between two Bernoulli processes. And he obtained a complete classification. Okay? So, now I think that is a good moment to ask if you have some questions on the lectures, either my lecture of this moment or Professor Lu's lecture of this moment. If you have some questions, something that has been too quick because unfortunately the material was very much, so we had to rush a little bit. If you have not some questions, yes, please.
Yes, thank you, Prof. My first question, Professor Lu was he gave two tables, one talking about the orthogonal polynomials and the same representation in the case of the quantum decomposition. And I was trying to get it clear.
Not the same, it's not the same.
It's not the same, yes.
He is what he called the L2 representation and the algebraic representation. L2 is the analytical, like Schrödinger. Algebraic is, like in my lecture, We start from polynomial algebra and construct algebra. But then these algebraic operators, a plus, a minus, a plus, when you realize you can realize as so-called pseudo-differential operators. In quantum mechanics, they are differential operators. And so you can ask, which other classical probabilities have the property that their creators and annihilators are not pseudo-differential, but real differential. And this class is not so wide. We have completely classified, but this is a rather technical, analytical problem. So I will not speak of this. But if you are interested, you can speak of it. Well, well, we can devote some of the tutorial, but I have to first explain the many other things before arriving to such a detailed expression. Why to characterize this? Essentially, it's related to very old problematic of harmonic analysis, which was the so-called Liouville operators, the Taylor Liouville operators. It's a very old problematic, and very, very deep and very interesting. And we now see the probabilistic meaning of this purely analytical approach. Okay.
I wanted to also know the interaction of the so-called the formation organization.
In quantum information. Well, in quantum information, you see, the quantum information is, of course, you can define, once you have the quantum approach and you have the states, you can define, you can associate quantum entropy to a classical probability measure. You can associate quantum relative entropy. So, you can do all quantum information, but in the new quantum mechanism, not only in the standard one. We have seen two, at the moment you have seen two examples of quantization. In physics they know two examples, Bose and Fermi. And we have uncountably many. Every probability measure, Bose corresponds to Gaussian. You have seen to Bose. Fermi corresponds to Bernoulli, you have seen today. And what is the other probability? This is open even if you have a single line. We have a lot of examples. For the most famous probability measures, we have begun to develop the corresponding quantum mechanics. But you see, even if you take very simple probability measure, the corresponding quantum mechanic is analytical. When you go to the analytical language, the beautiful new operator appears. I anticipate that with the free probability we will find the Hilbert transform, which is another very, very, very standard topic of study for harmonic analysis. Yes. You see, very standard. And you will see. But this is all deduced. We don't put by hand. We deduce.
Now, in Professor Ayoo's lecture, he made use of the multiplication operator.
Yeah.
And then the function was taken from Hilbert space.
Hilbert space is L2. L2 of the distribution of the random variable. Multiplication operator is the random variable.
Okay.
In this morning, my lecture, I explained that every random variable can always be represented in what the physicists call position operator and mathematics call multiplication.
Yeah.
Every random variable is completely universal. Okay.
Somebody has a question.
Why
Look at your speaker on the table.
Yeah.
Sorry, why are you discussing the money?
Cannot hear you.
Yes. Can you hear me?
Yeah.
Yes, why are you discussing the money? You discuss about cubic space. Cubic space.
Yes, yes.
So why are you discussing, we talk about m some sequence, n less than equal to n. And the polynomial algebra also is less than the result and the subscript of polynomial n. Now, that's
N, what I wrote.
We are talking about increasing sequence, like an filtration. Yes, I want to ask, in the case of, since we are talking about increasing sequence, do we have any case of decreasing sequence?
And of course, in probability there is also, and this is decreasing filtration are related to time reversal in probability. But here, the increasing is related with the degree of the polynomial. And there is no polynomial that is negative degree. This is not a polynomial. So the filtration must be increasing because it's naturally associated to polynomials. See, in the usual boson quantum mechanics, you have the Hermite polynomial. Famous Hermite polynomial, which are the orthogonal polynomial of the Gaussian. And they are an increasing filtration. Then,
Yeah, people, the participants are requesting for the lecture notes.
yeah, I can finish.
Okay, send to me. Okay. Then Professor Luke needs to send his own too.
Yes.
Yeah, so that they can
Professor
have.
Lu will send, he will send now.
Okay.
And so you can.
I can distribute.
And also Professor Bukas and Professor.
Okay, yes, Lucas Associate also should send so that
Yes,
you can
yes.
have.
Everybody will send
okay.
to you.
It's okay.
Yes. So you can reflect.
Reflect, yes, before
and,
publishing.
yeah, and think about it and put some other questions.
Yes. Somebody wants to know the importance of using the annihilation and creation operator in the formulation of these concepts that we are using. The importance.
Aha.
Yes.
Hey.
Yeah. The
Well.
importance of using annihilation
Okay.
and in your case, preservation operator.
Yeah, this is the main topic of my and Professor Lulek. Professor Lulek will show how to use algebraic constraints like generalization of Pauli constraints, Pauli exclusion principle. So Professor Lu will be concerned with the generalization of Pauli exclusion principle to create non-trivial interactions. And he will introduce, and he already introduced the notion this morning, but very quickly, maybe we can ask him to repeat the notion of Bernoulli interacting force space. I don't know if we, there is another question.
Looking at the tensor product of two measures, now the possibility of tensor products.
Product measure.
The tensor product.
Yes, how possible
It's product measure.
That's product measure.
not tensor product.
It's the product. We call it the notation. It's not.
It's product measure.
It's the usual.
It can be
But that's
cross
the definition.
Yes.
This is the definition.
That's the definition.
You see, it's the definition of a tensor product.
You can see it in probability
It's not
by-
really the same
by-
But in probability theory,
It's different. It's different.
you have a classical probability, because in probability theory they don't use tensor notation.
And you cannot
They use a
define
simple
like
problem.
homomorphism like this.
It's a notation. But this notation is useful
Integration.
because if you remember my talk this morning,
It is not.
I say you have the integral with respect to this probability. And this is what in quantum language is called a state. The integral with respect to a probability measure is a state. So when you want to use the algebraic language, the product measure go into the tensor product of the state. And now it ends up production be algebraic. So this is a lecture, this notation anticipates the algebraic formulation of classical problems.
In harmonic analysis, you define measure of the integral R measures.
The product measure is a standard notion in classical.
Yes.
It's actually defined with rectangles.
Yes, on rectangles, really.
Right, these are the rectangles.
The rectangles, yes.
Yeah. And then you have to prove a lot of theorems.
These are
The extension theorem.
Yes.
For measure.
Now two.
By the way, the extension theorems for measure are, in the functional analysis interpretation, the prototype model on which extension theorem in functional analysis are proved. And what is the most famous extension theorem? The Banach theorem.
Sure.
So, Banach was born as a generalization.
The extensions.
Yeah.
You see now.
They are laughing.
They laugh.
Prof, let me just start with comment. A comment. This is for our students. So please, for our students, nobody should have any kind of asking questions, no matter how trivial. If you allow the people in front to be asking the questions, the people going higher and higher. But if you come to the left and ask questions, you have also to come and bring it out in a beautiful way. So don't just keep quiet and be lost.
If you don't ask this question, you will not
You can see the thing going at the highest part, and you will be thinking everybody is copying and following. And always can give every example that links whatever you say. But it's not as one as the rest of it. So please let's talk and interact. In fact, this also is for interaction. Don't mind, because they have asked me what is the level of people that are coming so that they can know how they can move the notes. But I can't say anyone's level. So please, if you have anything in mind, say it, don't let it go. I'm also learning when you ask.
Leah,
Yes.
I will decide one Leah.
Only my reason.
Right. How much information is contained in For example, product measure will see that contains little information more than the single one, because it's a product that is best. But if it's not a product, can you, if you have a can we have a hierarchy to say which contains more information, which contains less? This is and the reality. We use reality. This would be there are differential operator with the analytical one, that's very difficult. And there is a lot of things to be done in this direction, because we know this analytical one is very slow. But let us see, there are other questions.
Yeah.
Okay, let us see.
He asked a question, then I will read this to you. So just let's see, okay. Then,
Thanks for the lecture. The question I want to ask is that using the concept of quantum can it be applied to energy quantization?
Energy
quantization. The concept of quantum probability, where we have the
yes.
Describe how electrons or lower.
Right.
so I have another question. You want to answer first?
Better.
Okay, you answer. Please let's be quiet. Yes. Yes. Oh. Now I understand. Okay, you can speak. You pick it. Just pick it. Can pick it.
So the question was if we can apply probabilistic quantization to some energy. So here to answer this question, we have to define precisely what is the meaning of energy. In usual physics, usual quantum physics, energy is defined through a self-adjoint operator with the spectrum bounded from below. Because typically energy is a positive quantity. So if the spectrum is bounded from below, you add a constant and it is greater or equal than 0. Okay? So what we can do, and I will give several interesting examples when I speak of the generalized quantum mechanics associated to the probabilistic approach. When I will speak of this generalized quantum mechanics, we will see that there are some natural Hamiltonians that appear in connection with stochastic processes. And this is a fallout in the usual quantum theory, because of the theorem that I will prove. I will call it, the theorem is called the democracy theorem. Democracy theorem means that all the random variables that we are considering, that is without zero norm vectors in the quantum decomposition, the quantum space, they are in some sense unitarily isomorphic. So what is the bridge with usual Hamiltonian system in usual physics? That using this isomorphism, you can take some Hamiltonian for which the equation, Schrödinger equation, is very easy to solve in one representation, in the canonical representation of one probability measure, but then you will use the isomorphism with boson and you obtain an integrable system. But the Hamiltonian of this integrable system, when you look at it not in the natural space, which is the probabilistic space, but you look into the Schrödinger representation space, it can be terribly complicated analytically. See? So this means that this approach will give you a huge class of non-trivial new example of integrable Hamiltonian system, completely integrated, using this isomorphism. So there is a fallout for usual boson physics.
But in your talk, some of them will come up and
I will cover this in my talk, but I will take the simplest Hamiltonian. For example, what is the harmonic oscillator, an analog of harmonic oscillator in the case, because it's the simplest Hamiltonian. And you will see that even in that case, we can explicitly find a solution.
So the second question from the equation is saying random variables are described by quantum states of C2 and C4 as in Professor Lu's lecture. He now says, is this correct and is this general?
It's not general, of course, this is an example. There are only two fermions.
So he says, if not, I have concerns with the case where so random variable problems are such that they have to be C3. They have to be C3.
Okay.
He says, if not, I have concerns with the case where some random variables,
new problems.
why some random variables problems are such that they have to be C3. You know, he uses C2 and C4 and in particular cases that he described.
No, well, when the answer is this. If you have a single random variable with real values, with n values, the L2 space is isomorphic n is. So C3 is contained already in one random variable, not Bernoulli, because Bernoulli has two values. But if you want three values, it's not Bernoulli. Okay? So it's not in the talk of Professor Lu. But was in my talk, because in my talk I said, when you have measure with a finite support, the L2 space is Cn for every n. So this includes C3.
Yes.
And if you have many Bernoulli random variables, you must have the natural, forget about now the analysis, but take just the algebra of polynomial in, say, not two, but three Bernoulli random variables. Well, since each Bernoulli random variable is a polynomial in one variable, and it is supporting 2 points, for the theorem I said before, the natural space is C2. So, if I have two random variables, the natural space will be C2 tensor C2, which is C4, and Professor Lu took C4. If you have three random variables, you will have C2 tensor C to C, which is isomorphic to C to the 2 power 3, and so on. You will have, for n fermions, you will have C to the 2 power n.
So I want to understand the Bernoulli random variable to be the random variable that are normally distributed in name one.
No, Bernoulli not normally. No, because it's discrete. Normal is continuous, but normal means Gaussian random variable. A Gaussian random variable contains values in all the real line. Not, yes, you remember the graph is like, correct, the graph is like this. So all the real line. But Bernoulli only two values. But they are the central limiting that I mentioned. Sums of independent Bernoulli normalized with the square root, their variance, in fact the square root of the variance, independent, they converge between two. So there is a bridge, but it's in the limit, not exact.
Not exact.
No.
Yes, Prof. But this is also for our students. Because he kept using the term odd moment, odd moment, odd moment. I know in statistics they use moment. Yeah, in physics they use moment. But in mathematics we use mean. So, Prof, my question is just for clarity. When you say all moments in the description of some of these properties, what do you actually mean?
Yeah, analytically it's very simple. I have written in my note, but it's better quicker to define. If you remember, I also gave one exercise, and I strongly suggest that you do this exercise. Analytical all moment means that, see, in random variables, we have the so-called numerical characteristics. Moments is expectation of power of the random variable. And if the random variable x has a distribution, probability distribution mu, when you write this, you apply the fundamental formula that I have written this morning, fundamental formula of classical probability, which defines distribution, and so this will be integral xn of mu del x extended to r with the real line. Okay? Yeah. So these are the moments. And now the problem is this: in probability, is a very famous problem that I will mention when we will arrive to maybe again another tutorial. But a very famous problem is called the moment problem. That is, every probability on R, so mu is a probability on R, with all moments. Remember, infinity means all moments. So every probability measure defines uniquely its own moments. Is the converse true? That is, if I give you the moments, can you recover the probability? This is a very, very famous, and even nowadays, 150 years after Jacobi, is no general. That is, we know that in general is not true. The answer is negative. That is, if I give you the moments, in general, it's not true that there is a unique probability. Okay? But in some important cases, many very important, this is true. For example, the Gaussian is true. The gamma distribution is true. Poisson distribution is true. That is why in classical probability we don't use moments, because to classify the numerical characteristic of a real valued random variable, in classical probability they don't use moments because they don't give unique answer. What do they use? So-called characteristic function, which is the Fourier transform of the distribution. So they use this expectation value of e to the power it. This, if mu is the distribution of x, this is called the Fourier transform of mu. And this always exists. And there is a theorem, important theorem of probability theory, that says that the given, so the random variable, you give the characteristic function. If the characteristic, and this characteristic function has two fundamental properties. One, it is continuous at 0. Two, mu hat of 0 equal 1.
Yeah.
And there is a theorem, important, non-trivial theorem, probability theory, that says that if you have a function mu, which is on the real line t belongs to R. If you have a function mu on the real line, such that it is continuous at 0, and mu0 is 1, then there is a unique probability measure. Such mu, such that this essentially, in this language, the function, instead of being a power, is an exponential. So we use this formula with exponential instead of power.
The unique real measure.
And so you understand why it's called the Fourier transform. If P is a density, if U is a density with respect to the Lebesgue measure, this is exactly the Fourier transform of the density. But this is defined for every probability measure. Okay. So this is the theorem that tells you that. So the converse is not true, but there are sufficient conditions. Different sufficient conditions. Essentially, they are on the growth of this moment. These are called Mn. Let us call M, depending on x, of course. So these are the classical moments, and there are many theorems in the called Carlson criteria, or essentially they are theorems on the growth of this number when n grows. They are famous theorems, also in harmonic analysis.
Yes. Yeah. In fact, if it has this property, the unique measure that you can get, you can, in some spaces, in harmonic analysis, can be equivalent to the radon measure.
To the
Radon measure.
radon. Radon.
Radon measure.
Okay, radon is a class of measure.
Yes.
Yeah. Yes.
It's on proof.
Yeah.
You can take it.
But this is included in the characteristic function. It includes all measures. We even define one with finite support, discrete support.
Yes.
Poisson, for example, is not exactly radon.
Yes, this is not.
So this is the how to say the.
Sorry, I want you to please write down explicitly what we call the moment problem. The moment problem. Can you write it down?
So yes. So you see, the moment problem is this. This is a very old problem. Many important mathematicians like Stiglitz, Hamburg, many Krein, many mathematicians gave contribution to this. But still now, as I said, there is no general, even in a single variable, no general. For example, there is an interesting criterion. Many books are written even recently on this moment problem. There's a huge debate. For example, if you can prove that this operator is essentially self-adjoint in L2,
Yes.
then the moment problem is here.
Okay.
But it is known that, again, there is no general technique. There are sufficient techniques like the Nelson criteria,
Yes.
but they are sufficient. There is no necessary and sufficient criteria, well, applicable. I mean, there is the von Neumann necessary and
But
sufficient.
if we just prove that it's essentially self-adjoint,
Essentially,
once you can prove that it's essentially self-adjoint,
if you prove that the multiplication operator by x
yes,
in the space L2 of mu
yes,
is essentially self-adjoint, then moment problem has unique solution.
it's okay.
But moment problem, you ask what is how is formulated. So One problem is given a probability measure P, mu, with all moments. Moments are defined like this. Then you define the moments. Then you define the sequence Mn of x, which is a sequence of numbers. X is real value, so the expectation of x, as you see from here, any power of x is a real number. So this object belongs to the real numbers. What is the fundamental property of the sequence of moments? The fundamental property of the sequence of moments is the following. And I suggest you to prove this as an exercise, a very simple exercise. Maybe if you have some algorithm. Yes, it's quicker. And it means better because it's not so heavy.
Go and bring that book. That way. Just a bit more. You want to say we need yes, that way.
Water is insufficient.
Just small.
This sequence is a very, very natural, very simple property. And let me try to prove this property. Suppose that I take one polynomial. One polynomial of degree and I consider the norm of this polynomial in Euler space. Of the probability measure. Then you see that I can write in the language of Hilbert scalar products. This is equal to sum of jk. And here I have a conjugate j. Then I have xj, xk, and I have ak. You see, because scalar product is necessarily antilinear in the first variable and linear in the second. But this is the scalar product in L2 of mu. So what is this? This is the sum over jk a bar j. integral O over R of xj times sk. Remember the fundamental formula for probability theory that I wrote this morning, times the mu dx. See? And this is your AK. But what is this? See, this is xj times ak is xj plus k. Let me write it explicitly so maybe you follow that. So this is equal, I can write it as sum, this is equal jk a bar j integral over r x j plus k mu ds. You see, you recognize what is this? This is the moment j plus k. So this is sum over jk a bar k, a by j, the moment of x of order j plus k, and here is a k. But the norm of any vector is positive.
Yes.
And we are assuming no norm zero, zero norm. So this is always greater than zero. So it means that the kernel defined by this, you see, this is a function of two variables, vector symmetric function. So this is this is the definition of the. If I call k this considered as a function of the two variables, k, x, j, and k. So the variables are integers, j and k. So this means that I have this property, sum over all j, k, from one, a finite sum, from 1 to some capital N, of a bar j of capital X, j, k, a k is always strictly, this means strictly positive definite. This matrix for each n, capital N, is strictly positive definite. If you remember my talk in this morning, I mentioned the notion of positive definite function. And the positive, if you consider this as a function of the integers, this is the definition of m to be a positive definite. So this very simple calculation shows that the moment function of x considered as a function of n is strictly positive definite. Okay? So this is a necessary condition. If a sequence mk is candidate to be the sequence of moment of a probability measure, then it must satisfy this condition. Otherwise, we know a priori it can be. So, the moment problem is, suppose that this condition is satisfied. Positive, strictly positive. Is it true that M gives a probability measure? This is the question. This is the moment. If I have a sequence mx, forget mx, m of n, such that this strictly positive definite condition is satisfied, can I say that there exists a probability measure on the real line such that the probability measure mu on the real line such that the moments of mu are these given numbers. Okay? And this is one problem which is simpler. The more difficult problem is when this probability measure is used. This is more difficult. And there is a huge literature on this. But why we don't care of this? That is what like we don't care of this because, as I said in my talk this morning, we don't complete the Hilbert space. We remain at algebraic level. And at the right level, the state of the polynomial algebra is always by definition. It's uniquely determined by the polynomial, by the monomial. So, in this sense, we develop a theory which, in some sense, we bypass this very deep analytical flow. Because we develop the theory at algebraic level.
Yes.
So, please, I want us to give Prof a round of applause for I know many of us enjoyed it.
Yes, sir.
There could also be many that enjoyed out of the way, but tomorrow you pick up yourself back. Tomorrow we will start early at 9, and since the package is set up, we wouldn't have any difficulty like yesterday. So please sleep well to have energy to be able to sit and follow the process.
I don't know why the day was very